And in this afternoon session, we prepared the session to specifically cater to the trend and the needs that we have seen, and to see how you can optimize the assay developed using some of the technical tips and tricks to be shared from LGC, as well as the live licensing capabilities going to be shared by Acumen. So without further ado, let's now introduce our first speaker for the afternoon session. That's Eugene Chow, based out of California. Eugene is currently the Senior Technical Sales Executive from LGC Biosearch Technologies. He has 20 plus years of experience in research, product development, as well as management, and technical consultation in PCRM molecular diagnostic in general, with a number of leading companies, including Roche Diagnostics, Bio-Rad, and Meridian Biosciences. So he's currently with LGC Biosearch Technologies as a senior technical sales executive covering both the North America and Asia Pacific regions. So Eugene has lots of experience working with the world's top 10 molecular diagnostic company, and it's time to hear from his expert tips on how you can optimize an assay, specifically point of care testing. Over to you, Eugene.
Thank you so much for the introduction, Joy. Hi, good afternoon, everyone. Can you all hear me clearly?
Yes, loud and clear.
Okay, great. Well, great to be with you all today. Thank you for joining us for today's event. I'll be sharing some recommendations and considerations that you may find helpful in the development of molecular diagnostic tests or products. Before I begin the presentation, I'd like to run a quick poll. If you are currently developing molecular diagnostic assays, please show your hands or raise your hands. Great, thank you. All right, let's begin. Now, the agenda today is to share with you the current IVD market trend. This includes not just molecular diagnostics, but all in vitro diagnostics market. And some of the challenges diagnostics developers will face in this area, and some of the ideas of optimizing molecular assays, as well as how us, LGC, can support you in this area. Now, if you look at the market from estimate from 2020 to 2027, you see the APAC region covers about
Eugene, just checking if you are there. We lost your audio. Can you hear me, Eugene?
21. Hello?
Yes. Breaking
Are
off a
are
little
you
bit.
able to hear?
Yeah, now it's better. Thank you.
Okay. Yeah, turn off my camera just to reduce the bandwidth. All right, let me go back to the slide. So the largest market will be North America. That's 39% of the market, as well as Europe, 34% of the market, trading about 5 to 6% growth rate annually. So from 2018 to 2027, the APAC market is estimated to grow to $30 billion by 2027 from 15 in 2020, almost double in this sense. So whoever is thinking about getting to this space, it's perfect timing. And of course, this data is a little bit out of date because they didn't foresee the COVID pandemic to happen. And now monkey pox is trending as well. So to develop a molecular diagnostic assay or product involves quite a bit of development efforts, and facing quite a bit of challenges from different aspects. The first thing is hardware capabilities. So for point of care device, or even if you're using qPCR instruments, the number of channels, or if whether it's going to include sample preparation, it's all really complex in terms of hardware development. And there's assay design considerations, depending on the kind of molecular diagnostic tests you want to develop. Um, the target organism sequences might not be as easy to work with, depending on the genes you choose to target. And thirdly, there's sample preparation considerations, whether you want to simply lyse the organism or you want to extract and further purify the nucleic acids. That will affect your cost, first of all, as well as the speed of sample to results. Can you all hear me clearly still? Yes? All right. And the fourth thing is selection of the enzyme and reagent that's used to run the assay to amplify the targets, sometimes even developing the formulation. And once you have all the previous parts figured out, there's optimization of the assay to achieve your desired uh, specs or assay requirements. And if you are developing a piece of hardware as well, then translating that optimized assay from a benchtop system to your point of care device is also another part of the challenge. And finally, if you had all the pieces together, then benchmarking your product against the market leaders, or simply a benchtop system that's used in a clinical lab to demonstrate its performance, sensitivity, as well as specificity will be important. And finally, launching of the product requires a lot of coordinations in your marketing efforts, as well as your market reach. And that's a different set of challenges. Any questions so far?
Any question from the audience? I think we are good for the time being. You can go ahead, Eugene.
Okay, thank you. So looking at the workflow, starting from the type of samples you're working with, if you are looking at looking to work with urine samples, stool, blood, saliva, and various sample types will have its uniqueness in terms of the way you want to prepare them and purify, dealing with inhibitors. So the next step will be simply extracting your nucleic acids, whether it's DNA or RNA, or thinking about further purify if your acid sensitivity cannot reach your desired target. And once you have obtained nucleic acids that you can target, the amplification part is another area where you want to consider the kind of method you want to use to amplify. Is it going to be a PCR method, or is it going to be an isothermal amplification method, or other modalities such as using CRISPR or even NGS? And detection-wise, a lot of times for infectious diseases, it's mostly qualitative detection. But for some viruses such as HCV, HIV, there are also viral load measurements to look at treatment effectiveness to monitor that. So that's also a consideration when you develop an assay. Now, to achieve the desired results and be competitive enough in the market, or simply develop a sensitive assay that's very useful to help screen, for instance, during the pandemic, there are various assay requirements that comes to mind. So to look at the assay performance, we can look at these 5 areas. The top is specificity, which is crucial. So there is no, sorry, cross-reactivity to similar um, or species or even within the organism, there are different clades, such as in HIV. You want to make sure you detect that the organism, the specific target that you want. And there is the sensitivity of the assay is important. How low of a detection limit you can achieve with the kind of sample type you're working with, the kind of sample prep methods you're working with, and the amplification method. And there is speed to consider as well. So a lot of times people want to get the results as fast as possible in uh, a kind of infection that can be transmitted through aerosol, through coughing, these droplets in the air, then a really infectious organism needs to be detected as soon as possible to control the spread. So a lot of times for that kind of purpose, the assay time is crucial to be as short as possible. Of course, the assay needs to be highly reproducible. So there isn't a lot of variabilities, whether you're working with nasal swabs or saliva or blood. And the thermal stability, this concerns the enzymes, reagents, as well as the fully assembled assay, whether it's in wet format or in dry format. So the stability of the assay in a high throughput clinical testing lab, that's quite important if you're running plates after plates in a stacked automated fashion. Any questions? No? All
I think
right.
we are good for the time being. Can just yes, thank
Right now, I'll share some ideas, tips and tricks on optimizing assays. And I kind of split mostly into qPCR and LAMP assay, but mostly it's going to be qPCR. So looking from the component aspect, first, this kind of sample type or templates you're working with, whether there are going to be inhibitors present, that's important for lysis based method. Of course, there are gonna be some residual inhibitors left in the sample, and that can be dealt with a reagent formulation or the kind of amplification method that you choose. And the quality of the sample can be important. In cancer diagnostics, a lot of times you're dealing with highly fragmented nucleic acids, such as the ones you collect from liquid biopsies, cfDNA, cfRNA, or from FFPE samples. And whether it's intact from the organism or it's fragmented from the cells, these things will affect various assay as requirements that you saw in the previous slide. And the purity is a crucial factor as well. Whether you want to use a lysate or purified nucleic acids, depending on the purpose of your qualitative or quantitative detection, this can play a key role in deciding which way you want to go. Now, to have an assay, first you gotta design some primers if you are working with a PCR-based method. So some of the considerations are the length of the primers you're using. It really depends on the kind of specificity requirement. Sometimes you want to catch all of the different uh, subspecies or serotypes of an organism, then having degenerate primers may be useful with specific probes. And when designing primers, you want to make sure there are not that many G's or C's towards the 3' end of the primers, because if you have too strong of a binding at the 3' end, it increases the stability of a mismatched hybridization, and that can cause amplification of non-specific targets. And the length of the primers and the GC contents will contribute to the melting temperature of these primers. So depending on the amplification method you want to use and your annealing extension temperatures, these all come to play when you design the primers and what kind of TMs they have. In a primer, you want to avoid more than three or more than three consecutive Gs for the same reasons of the second point where non-specific binding can cause non-specific amplification when there's highly stable Gs and Cs in the sequence. Now, when you look at the TMs of the forward and reverse primers, you want to make sure the difference between them is not going to be more than 3 degrees Celsius. So they can both bind around the same time as efficiently and amplify well of your target sequence. And if you are able to match the number of Gs in the forward and reverse primers, that will help them bind efficiently and specific as well, and to increase that amplification efficiency. And of course, you want to avoid self-complementarity within each primer, as well as whether different primers you have in the assay, if you are multiplexing, they don't form primer dimers easily because they're complementary in sequences. And to optimize, once you have taken all the considerations mentioned above, you titrate them with the probes. If you're using a probe to detect, to make sure that the assay is sensitive, specific, and with the speed of the fastest time you wish, um, and choose the least amount of the Parmesan probes or lowest concentration that can provide the best performance. And if you're working with probes or fluorescently labeled oligos, the binding site of the probe should be close to either the forward or reverse primer on either strand. So as soon as the primer sits down, it starts amplifying, and whether it's displacing the probe or cleaving the probe to release that signal so it can be efficient. So the length of the probe is in general recommended to be somewhere between 20 and 30 base nucleotides. But this really depends on the kind of fluorophores you want to use for reporting, for signals, as well as the quencher you want to use, because the distance between the two um, will affect the quenching efficiency to reduce that background. And the target specificity, if you happen to have a lot of A's and T's, maybe you want to lengthen that probe a little more to have that specificity and with increased TM. And the quenching method is important as well. So single quenching versus double quenching, such as the BHQ or black hole quencher, label on one end to quench, or you have an internal quencher like in the BHQ Nova technology to reduce that background, basically to increase the signal to noise ratio. So for probes that are longer than 25 nucleotides, it's recommended to have dual quenching or have an internal quencher within to reduce the background and increase that quenching efficiency. So the TM of the probe should be somewhere in between 6 to 8 degrees Celsius higher than the TMs of probes. The reason being you want to make sure the probes sit down on your target sequences before the primers come along to make sure you can generate that fluorescent signals. Otherwise, if the TMs of the primers and probes are similar, then you can be extending the primers without the probe sitting on your target sequence, then you're amplifying without any signals generated. And one thing to be mindful is wherever you choose to label your probe, whether it's the 3' end or the 5' end, oftentimes on the 5' end, there isn't a G next to the labeling base because G can quench the fluorescent signals. So if you chop off the probe, separating the quencher and the reporting fluorophore, the G next to that fluorophore can reduce the signal, and that can cause lower assay sensitivity. Now, obviously, magnesium needs to be optimized as well, and the usual range in master mixes, or if you're developing your own formulation, is somewhere in the 3 to 6 millimolar range. And you can to titrate them, you can titrate them in 0.2 to 1 millimolar increments to fine tune that. Regarding the amount of enzymes you want to use, the DNTPs, even enhancers or surfactants to make sure that nothing absorb to the plastics or cartridges you have, or simply just in your tubes that are commonly used. These things will need to be titrated to achieve your the performance specs you want. Uh, and the amount of enzymes in the reaction uh, can contribute to how fast the assay can run and how much products are being amplified. So that is something you can play with to increase the assay, reduce the assay runtime or increase the assay speed. Now, if you're planning on drying down or developing room temperature stable products or assays, or lyophilization or freeze drying, another term, some of the bulking agents such as the various disaccharides or cryoprotectants that can reduce the harshness of freezing in to the enzymes or the lyoprotectants to protect the enzymes from not having water around will need to be optimized to make sure that the lyophilized materials will be stable for the desired length of time. Typically, if a lyophilization is done properly and well, you can expect um, the assay, which includes all the enzymes, the different components that are required for amplification, as well as the primers and probes in there to be stable for at least 12 months. So optimizing the concentrations of these so-called excipients so you can maintain that post-lyophilization performance. And the buffers you want to use, in general, it's recommended to use histidine or tris buffers to minimize the amount of to minimize the variability in pH during freezing. So phosphate buffers are not good for this purpose if lyophilization is the end goal, because the pH varies quite a bit in that kind of buffer during freezing. Any questions?
Questions from the audience?
No?
We'd
All
like to
right.
proceed. Thanks, Eugene.
Sure. And PCR cycling parameters is also key in terms of assay optimization. So the typical three-step cycling with denaturation, annealing, extension um, can be adjusted to help achieve that fast assay time and the sensitivity. Now, typically, if your sequences don't have a lot of G's and C's, which doesn't require a longer time to peel them apart, then the shorter amount of denaturation time is desirable. And annealing temperature, as most of you or all of you know, is a key in optimizing PCR or qPCR performance. So you can reach that high amplification efficiency, high yield, and especially the specificity of it. Because if you have a lower annealing temperature, the primers and probes are easy to bind, including mismatches, and that can cause non-specific background being amplified. So achieve that high yield early detection, optimizing this is important at the annealing temperature. Typically, you start with 5 degrees Celsius below the lowest TM of a prime pair that you have in the assay. And a lot of times these days, people are using the so-called two-step PCR, which combines the annealing step and extension step. And due to commonly used programs out there for primers and probe design, this is what a lot of us are using these days. And that's because the TM of the primers in general are greater than the extension temperature. But that's not the case, then the three-step PCR might give you better efficiency. And for extension, the temperature is usually in the range of 60 to 75 degrees Celsius, and optimizing the temperature of extension as well as how long you want to extend your amplicon. This will help increase assay sensitivity and reduce the time you need to reach a detectable signal. Right. So in a PCR or qPCR based assay, the amplification efficiency is quite important. Not just important in single plex reactions, but really important in multiplex reactions. And oftentimes, if you have a control reference assay in the reaction, that abundance of the templates can kind of consume the resources of the master mix and the various components that can reduce the amplification efficiency of some of your target assays, and in turn that reduce the sensitivity of your targets. So looking at the efficiency in a multiplex assay is very important, and you can do so by diluting the templates 1 to 10 serially to generate a linear regression curve or Senna curve. And you want to do that to obtain the slope. So the slope is how you can use to calculate the efficiency, which is 10 to the negative 1 divided by the slope minus 1. And this will give you the percentage or how efficient it is that you amplify. And in PCR, it's a doubling effect. So this will help you identify whether you want to reduce the amount of primers and probes of your internal control, or redesign the primers and probes of your internal control to actually artificially reduce the efficiency to help boost your target sensitivity. And to make really efficient reactions, the amplicon size for qPCR is stay within 70 to 155 base pairs will be best. And this is the end of the qPCR assay optimization section. If you don't have any questions, I'll move on to a quick isothermal lamp-based optimization slide. All right.
Yeah, good to move on. Thank you.
So there are various isothermal amplification method. LAMP or loop-mediated isothermal amplification is one of them. So the same kind of considerations for the type of samples you want to use, the quality of sample as well as purity will affect the assay performance, just like you saw in the qPCR section. And these are some of the recommendations. When you design LAMP primers, um, you can design 4 primers, so 4 primer reverse, 4 internal and reverse internal primers. Just 4 can allow you to amplify your target in LAMP. But it's highly recommended to include the loop primers, so 4 loop and reverse loop primers to get the fastest detection time and the best performance. And typically you want to design 3 to 5 sets of these 6 primers. And we recommend using the Premier Biosoft's LAMP Designer software to make your life easier in designing these many primers per target. And because it's isothermal reactions, the temperature is staying the same during the entire reaction time. The reaction temperature is one thing you can optimize in isothermal amplification. And this really is similar to the annealing temperature in PCR or qPCR, where it affects the specificity and stringency of the amplification condition. Magnesium and the amount of enzyme you use, and the concentration of primers, as well as probe, that if you want to use fluorescent-based detection or double-stranded DNA binding dye, and these are the various components you want to optimize and titrate. Questions, anyone?
I think we are
No?
good. Thanks.
All right. So how LGC can support you in development, whether you are developing a clinical lab assay, or you are simply developing various assay kits. So these can be run on conventional qPCR benchtop platforms or a novel point-of-care device. This is where a lot of our clients really rely on our mission-critical components and solutions. So under the LGC Biosearch technology umbrella, um, the top 10 diagnostics companies globally source our clinical grade or GMP oligonucleotides, primers and probes, and even getting the oligo synthesizers from us, buying control port glass for these so they can synthesize their own primers and probes. And sample preparation, whether it's magnetic bead based or column-based purification, are in DNA extractions. Um, that's also what a lot of people use in their clinical testing labs, as well as the rapid fire qPCR reagents and the lava lamp lamp reagents that they use. And for high throughput clinical testing labs, such as in UK during the pandemic, they use our NextR platform, the ultra high throughput platform for COVID monitoring and screening and detection. So we have the IntelliCube qPCR systems, the high throughput PCR platforms, as well as automated extraction systems such as the Octapure, and these are the various tools are available to you. In terms of enzymes and reagents, we have developed lyophilization compatible enzymes and reagents. And depending on the kind of targets you're looking at, for DNA targets, the rapid-fire qPCR5X master mix, the hostile attack enzyme in this master mix, if you wish to develop your own buffer formulation, as well as for isothermal amplification, the BSD DNA polymerase that's lyophilizable are available to you. And if you're detecting RNA targets, such as a lot of the RNA viruses, the rapid-fire LyoFlex, our newest addition to the rapid-fire family, the LyoFlex one-step RT-qPCR5X master mix is highly sought after because of its heat-activated RT. That allows the specificity during the RT step. And the rapid-fire one-step RT-qPCR system and the EpiScript RT, thermal stable RT are being used in this space. And our proprietary lava lamp enzyme, that's a single enzyme that can amplify both DNA and RNA. So it doesn't require an additional RT, but the enzyme itself can reversely transcribe and amplify the subsequent complementary DNA. Now, in addition to these catalog items that you saw in the previous slides, a lot of our diagnostics clients are really keen on using our customization solutions. So you have various options to customize these reagents, from reconfiguring the existing enzymes reagent in terms of the dispense size when you receive, that's convenient for your production in different vessels or plastics, even private labeling. Two, changing the amount of enzyme that's present in the master mix to increase the amount of enzymes. And it's not just in these PCR master mix, but in, let's say, an NGS assay, you want a higher concentration of the T4 DNA ligase. We can help customize in the kit components and the enzyme concentration as well. And we are very open to co-develop new or custom reagents and developing new formulations with you to help you bring your products onto the market.